Okay, we're going to jump into today's lesson by first looking at this slide that references the concept breakdown, the limit definition concept breakdown that you needed to go through. Okay, so this is a picture of 2 points on a curve, x comma f of x and x plus h comma f of x plus h. And we're finding the average rate of change between those 2 points. So we have, here's y2, here's y1, here's x2 is x plus h, and then x1 is just x. This simplifies down to this. This is finding the average rate of change between 2 points that are getting closer and closer together because the difference in x values of those 2 points is h. So if we look at this next picture, okay, this is when h is equal to 2. Okay, the difference between x and x plus h is just a difference of 2. And when we take our limit, we're going to let h approach 0. And we can see how the points get closer and closer together. So then, as we've continually talked about, when the 2 points are basically right on top of each other, now we have an instantaneous slope. But before, it was the instantaneous slope at a specific x value, and this is just the instantaneous slope at x. So what we do is we take this limit with f of x plus h, here's f of x plus h, minus f of x, all divided by h, all right? And what we get when we evaluate this limit, we multiply by the conjugate, just like we've always done with square root problems like this. And then we cancel some stuff out. X minus x is just 0, and 5 minus 5 is just 0, so we're just left with h. These h's cancel, and now we have 1 divided by root x plus 5 plus h plus root x plus 5. But at the very beginning, we've always said that h is eventually going to approach 0. So when h is 0, we can just get rid of h, right? Because we're plugging in 0 for it. So then we get root x plus 5 plus root x plus 5, which is 1 over 2 root x plus 5. So we call f prime x the derivative of f of x. F prime x equals 1 over 2 times the square root of x plus 5. And this is going to tell us the slope of f of x, which is square root x plus 5, at any input x, any input we want, okay? So what we find is if we plug in x equals -4, okay, here's our function square root x plus 5. Again, here is the work for finding f prime x. You want to make sure you have all these steps copied down, and they should have been in the concept breakdown, so you should already have it. But here are the steps for finding f prime x. So what is the slope of square root x plus 5 at x equals -4? Well, we plug in -4 and we get that it's 1/2. Okay, so then at x equals -4, the slope of the curve is -1/2, is 1/2. Okay, what about at x equals 4? Plug in 4 to f prime x, we get the slope is 1/6. So at x equals 6, the slope is 1/6. What about at x equals -1? We plug in -1, we get 1/4. The slope at x equals -1 is equal to 1/4. Okay, and then what about at x equals -5. Well, if we plug in -5, our derivative is 1 over 0, which is undefined, and the slope is vertical at -5, which we can see visually. If we try to draw this tangent line, we get a vertical slope, and vertical slopes are undefined because the run, if we're vertical, is 0, and dividing by 0 produces an undefined value. So the idea here is before, if we wanted to find these different slopes, we would have had to set up different limits. So our instantaneous slope formula, if I wanted to find the slope of at x equals -4 of f of x equals square root x plus 5, I would have had to do the limit as x approaches -4 of square root x plus 5 minus 1, because when I plug in -4 to this, I get 1, and that's divided by x. Okay, we'd make it minus -4, so x plus 4, right? And we would have to evaluate this limit, and when we do that limit, what did we get again? We plugged in -4, that was the first one we looked at, which was right here. Plug in -4, we get 1/2, and we would get 1/2 if we did it this way as well, right? But then if we wanted to find the limit at x equals -1, well, or let's do at x equals 4, we would have to do the limit as x approaches 4 of square root x plus 5 minus 3, because if we plug in 4 to square root x plus 5, we get 3 over x minus 4. And we'd have to evaluate this limit like we used to, and we would still get an answer of 1/6. So what this process does is it allows us to just do one limit to define a function that we call the derivative And within this derivative, we can plug in any x value we want, and it will give us the slope of the function at that x value. So now we don't have to do all these different limits to find these slopes. We can just do the limit one time and find a function that will do the work for us. So the limit definition of a derivative, which you should have in your notes, is this guy. The limit as h approaches 0 of f of x plus h minus f of x over h. This is going to allow us to construct a function that will give us the slope of f of x at any x value, because we're taking one generic point x, one generic x value x. We're creating another one by adding a little difference to that x plus h. Now we have two y values. The difference in the x values is just h. If we let this go to 0, this will give us the slope of the function at x, any x value we want. So the next part of the lesson is going to ask you to apply this to two new functions. Okay, so you're going to apply the limit definition of a derivative to 1 over x and to square root 3x plus 1. And we're going to use that limit definition to define our f prime x, and then hopefully find the slope at 4 and 6, and then the slope at 1 and 5. So moving down here, okay, this is just f of x plus h, right? That's f of x plus h. This is f of x, and then obviously we have h on the bottom, right? So our function was just 1 over x, so f of x plus h is just going to be 1 over, instead of writing x, we're going to write x plus h, okay? Minus, our function was f of x was 1 over x, we already had that, and then over h. So now this is a limit that we already have the algebraic tools to solve, because we've dealt with finding common denominators before. So we have to multiply by x over x, and we have to multiply by x plus h over x plus h, which takes us to this step. Okay, so now we have x minus x plus h on top. We have our common denominator, we have h. Okay, x minus h, right? X minus h, because we have to distribute that negative. So x minus x is just 0, and we're left with a minus h on top. So we have minus h on top, x times x plus h over h. Okay, these h's are going to cancel, leaving us with just negative 1. So our final answer is negative 1 over x times x plus h, which when h goes to 0, which it does in this limit, it was the limit as h goes to 0, that just leaves us negative 1 over x times x, which is negative 1 over x squared. Okay? You may remember from doing patterns like this that, okay, let me give you an example. If we did the limit as x approaches 3 of 1 over x minus 1 over 3 over x minus 3. Remember the pattern, you guys would call this b, and you would say the final answer to this is negative 1 over b squared, which is negative 1 over 9. Well, now we've proven that relationship here, right? It's always going to be negative 1 over x squared, right? Whatever we're plugging in for x in this case. So the derivative of 1 over x is negative 1 over x squared. So what is the slope of 1 over x at x equals 4? Well, it's negative 1 over 16. What is the slope at x equals 6? Well, it's negative 1 over 36, okay? Highly encourage you to go back and look at these steps and understand how to get the derivative of 1 over x using the limit definition. And if you're ready, though, we will continue, and we'll go down to the function 3x plus 1, square root 3x plus 1. So in this function, we have f of x plus h, which just means that we're going to replace x with x plus h. So instead of writing root 3x plus 1, we're going to replace x with x plus h. And then f of x was given. So now we have to do the same thing we've always done, which is multiply by the conjugate. Notice the conjugate down here. Okay, this is the conjugate of the numerator. In the numerator, multiplying by the conjugate just gets rid of those square root signs. And this is minus all of this, so it's minus 3x minus 1. We distribute that negative. Okay, that's good, because then we get 3x minus 3x is 0, and we get 1 minus 1 is 0. Okay, distribute this 3x, 3h. And this simplifies down to 3h. And then, oh, the h's cancel now, right? So we have h on top, we have h on bottom, so those go away, they cancel. Okay, so we have 3 on top now, and then we have our conjugate in the denominator, right? So now we can simplify this, because once again, we know that h is going to 0, so we can just have that disappear. So we have root 3x plus 1 plus root 3x plus 1, which is 2 root 3x plus 1. Okay, 3 still on top. So now if we want to find the slope of the function x equals 1, we'll just plug that in, get 3 over 4. If we want to find the slope of the function x equals 5, we just plug that in, we get 3 over 8 when we simplify. Okay, so now we can find the slope of the function square root 3x plus 1 at any x value we want using this function, which we call the derivative. So now we want to start to examine some patterns we're seeing within the derivatives. So if we look at just quadratic functions in general, like x squared, 3x squared, and 4x squared, okay, we already know the derivative of x squared is 2 times x. And we can use that, we can use the limit definition of derivative to prove that, right? So here are my 3 functions. Here are their derivatives based on the limit definition. So we have f of x plus h minus f of x over h. F of x plus h minus f of x over h. Okay, well, let's see how these simplify. So x plus h squared, we have to be careful with. We have to FOIL it. So it ends up being x squared plus xh plus xh plus h squared, which simplifies to this, x squared plus 2xh plus h squared. Okay, we subtract x squared, and because that's f of x, and so then x squared minus x squared is just 0, so we're left with 2xh plus h squared over h, but we can now factor out an h, so we get h times, maybe not blue, how about green, h times 2x plus h, but then we have an h on top and an h on bottom, so those h's cancel, and we're just left with 2x plus h. Where does h go? H goes away because h is approaching 0, so we're just left with 2x. Okay. I want to recognize that these other two are basically the same, except for the coefficient 3 and 4 out front. Okay. Notice that x plus h squared is still x squared plus 2xh plus h squared, but then we have to distribute our 3, so we get 3x squared plus 6xh plus 3h squared. Okay, 3x squareds go away. 3x squared minus 3x squared is 0. And then same idea here, 6xh plus 3h squared, we can factor out an h just like we did before. So then this cancels to 6x plus 3h, which is just going to be 6x. And then same thing here, except there's a 4 out front. So we distribute our 4, get 4x squared plus 8xh plus 4h squared. Okay, 4x squareds cancel. One of the h's cancels, so then we get 8x plus 4h. Okay, h goes to 0 again. We have 8x. Okay, this work has been brutal, but the reason we're doing it is because we're trying to see a pattern that's going to make us do less work in the future. So if we look at our answers, here's f of x, here's f prime, here's f of x, here's f prime, here's f of x, here's f prime. Hopefully we can start to see a pattern, right? We're just multiplying by 2, multiplying the coefficient by 2, and then dropping 1 from the exponent. So now the derivative of 4x squared is 4 times 2x to the first, 8x. Okay, here's some more examples, maybe. Okay, I found them. Here they are. Here we go. So if f of x is 11x squared, f prime x is 22x. If f of x is 15x squared, f prime x is 30x. 101x squared, 202x. We're seeing the pattern for the derivative of quadratics that we can now use. Instead of doing the limit definition, I can just use this rule to always find the derivative of quadratics. So the question is there going to be something similar for cubics? And that's what we will discuss in part 2 of this lesson, which is also linked in the slideshow. So go back and find that link.